Morning everyone. So here's actually starting off with some new material. This will be the end of our chapter 2 unit on atomic structure. So again, I encourage you to have out your notebooks. That way you can be following along as we go through this. We're going to basically go from the Bohr model, see places where it isn't able to make good predictions, and we're going to talk about doing a new model called Electron Configuration. You're going to find on this handout section here this energy level diagrams that we work with, as well as the summary periodic table that we're going to get to shortly. So just for starters here, as we begin, as we build this newer model here, first question is, well, why do we need a new model? Where are places that the Bohr model actually breaks down? This model here is called Electron Configuration, or Electron Config. We're going to start off just saying, well, the Bohr model, the whole notion of having protons and neutrons in the core, electrons in different shells, a lot of it is very predictive. A lot of it we're going to use back in chapter 4 when we do our bonding again. But we're going to start off, the Bohr model has some limitations. Has some places where it actually doesn't make the appropriate predictions. So has some limitations, as probably the biggest thing here is electrons are not in orbit around the nucleus. That's not actually what they're doing. So the story we've been told so far has been a little bit of a simplification. We need to see what the electrons are actually doing. Now, it's not a bad thing for us to have learned the Bohr model over science 9, science 10, and whatnot. It does make some good predictions, but as we do step into the newer concepts in grade 11 and grade 12, we're going to see the places where it breaks down. So it's a little bit simplistic to say, yeah, we have protons and we have neutrons. That part there is just the same, but the part that we're going to be addressing is how the electrons actually get added to outer shells. We started talking about electrons can be on different shells. We use n for the number of shells. We saw from our quantum theory that every shell had a certain maximum number. If you just quote from me here, let's say shell 1, shell 2, shell 3, if I make a quick max number of electrons, and based on the shell number, you should be able to fairly easily list off, well, the first shell maxes out at 2, second shell maxes out at 8, third shell, depending on how you say it, I would say 8, but you could also say 18. We'll finally get an answer of why is it sometimes 8, why is it sometimes 18. And we actually need this electron configuration model to actually explain it. We are going to be using the analogy, electrons are like guests at a hotel. So every element will have a certain number of electrons. They're going to be entering, because electrons have a negative charge, they're going to be trying to enter shells closest to the nucleus. We assume what's called ground state. We saw that term a little bit with our nuclear chemistry from yesterday, but in this case here, ground state basically means electrons are as close to the nucleus as possible. Electrons enter closest to nucleus as possible. And they'll only go to outer shells as the inner shells end up getting full. So, for example, the first one goes in, it's already there. We talk about the second one here, has a little bit of a decision. It also wants to be close to the nucleus because that way it's close to the positive charge center. But unfortunately, there's also some repulsion between the other electron. It's always playing this compromise. Well, do I like the nucleus more, or do I hate this other electron more? The end of the story is we end up getting paired. It's always best to be on shell 1 to have things paired up. As we get to a third electron in, just based on the regular Bohr model, this is when we started saying, well, the first shell is full. We're going to start going single, single, and we'll see some of these ideas come back as we do our new lesson. So, as we start modifying and creating this newer model here, we're going to work with this idea. Each of these energy shells, these energy levels are what are called quantized. Energy levels are quantized. But here's the first modification we're going to change is that these shells, these n values, n is 1, n is 2 for the different orbits, the shells can be subdivided into what are called subshells. The subshells are given very funny letters. These are just placeholders for the orbitals that we're going to talk about. We're going to use the placeholders S, P, D, and F. They do have some semblance. For example, F stands for fine, When we look at the line spectra, the sort of the line that we get from that is a very fine line, it's very clear cut, okay? But aside from that, you can just use it as a placeholder. And essentially, here's our idea. If we go back on our energy level diagram, our energy level diagram for being on shell number 1, shell number 2, shell number 3, we're going to basically say the electrons on these shells here, even though I'm maybe electrons, let's say we're both on shell number 3, but we may not actually be exactly in the same energy. So this is so far still the Bohr model, and we're going to slowly start making changes to our electron configuration model. First shell is still fairly boring. The first shell doesn't subdivide at all. When you have n equals 1, the first shell is only one room available for electrons. I've written these letters here in order of increasing energy. S is the lowest energy, then P, then D, then F. Because 1 is relatively low energy means stable, the one room here I'm going to call it a 1s subshell. The 1 refers to we're still on energy level 1. If you think about floors on a hotel, we're still floor number 1, but the kind of room that we're in is an S subshell. We're going to come back in a later lesson this week to talk about the shape of the actual subshell. When we start seeing the subdivision and starting off in shell number 2, back in the Bohr model, we would just add things single, 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 single. They all look equal distance away from the core. We're going to see that in the mirror model, this shell number 2 is actually subdivided into two parts. The lower energy part is called the 2s subshell. The higher energy part is called the 2p subshell. Both of these are on energy level 2. Thinking about that floors of a hotel analogy, we're all on floor number 2. But just because you're on the same floor doesn't necessarily mean that all the rooms on that floor are equal distance from the core, equal energy from the core as well. You're going to find that when shells here, as they start separating, they're always going to be in the order S, P, D, F. The lowest one will be S. The next one comes as P. When we eventually get high energy enough, like shell 3, shell 4, we will eventually get into the D's and F's. But so far, this is how things split. So shell 1 doesn't split, just one S. Shell 2 splits into two possible layers. That means electrons would be a little bit more stable if they were on shell 2, because that one here is energetically a little bit less energy than the 2p. You'll also notice that as I've drawn the 2p kind of rooms, anytime the p shows up, it actually always shows up as 3 rooms. I know this is getting a little bit funky as well, but just hang in there. You're going to see sort of where the places that it actually matches up with the Bohr model, and what else does this help us predict for later. So far, shell number 1 doesn't split, shell 2 is separated into 2 layers, shell 3 very similarly, it's going to separate into 3 layers. The lowest energy layer is called 3s, the next energy layer here is called 3p, and then we're going to eventually, because shell 3 is now further from the core, we're going to eventually get shell 3d, and each of these lines that I'm drawing will eventually be called an orbital. The orbital represents a kind of room where the electrons can actually sit. So the big idea from this section so far has been we take one energy level and we basically start separating them into multiple layers. Let me just recap those placeholders again. We do S, P, D, and F. We are increasing energy as we go in that order. So this is increasing energy. And not only do we need the higher floors on the hotel before we get into these really high shells, we're going to see that every time these orbitals show up, they always show up in discrete numbers. So for example, the S kind of room on any floor, we see floor 1 had an S, floor 2 had an S. S only comes as one, what we're going to be calling orbital. So far we've been saying shell for the energy, the orbit that we're in. Subshell is now what we're subdividing in. We can compare orbit now to the word orbital, and an orbital here implies a room. The P, in a similar fashion, whenever the P type of room shows up, they always come to us as 3 orbitals, the D kind of rooms as 5, and the F kind of rooms as 7. So we're starting to subdivide the different shells, we're starting to get some detail into, oh, the electrons on these shell 2, shell 3, they're not all the same energy distance. We will come back, like I mentioned in a later lesson, to actually draw these orbitals. But for the time being, we're just going to use them as placeholders. So, I'm just going to show you how this model works out. There's a couple other rules that we need before we can look at a few examples. The first rule that we're going to do is something called the Aufbau principle. Aufbau, I'm told, in German means building up. Those of you that speak German can verify that. So, Aufbau principles, we've been doing this all the time. If we assume things are in ground state, electrons are always entering closest to the core, we're going to use this notion, electrons always enter orbitals. This time it's not just the shells, this time it's, are we in S room or an F room or D room? They enter orbitals the lowest energy first. That's sort of like saying, well, electrons have a negative charge. If there's spots close to the core, the electrons will go to those shells first, and we're going to build up from there. We always assume ground state. If we're not in ground state, we have an excited state, just like electrons can absorb energy and be at a much higher orbit. Even in this electron configuration model, it would be the same. Just before we get to another example here, the second rule that we're going to do is something called Pauli's exclusion principle. We are getting into a little bit of quantum theory here. There's a lot of research going behind justifying why these rules are there. We're just doing the, okay, so since these rules, since atoms behave in this fashion, we're going to be able to just answer questions inside. So, Pauli's exclusion principle says each one of these orbitals, each one of these rooms, the S kind of rooms, the P kind of rooms, D and F, each orbital has a maximum, just like the shells had a maximum. In this case here, we're saying each orbital can hold a maximum. This is an absolute highest amount. These rooms here can only hold a maximum of 2 electrons. And electrons have this funny property called spin. When they enter the room itself, the electrons actually have to have different spin. The analogy that I have for you for spin, we're going to refer to an electron, pretend that this is the planet Earth. The planet Earth is sort of rotating along the axis. Let's say it's rotating in one direction. We can refer to that, maybe it's my electron that's twisting around in that direction there. We can refer to that as a spin-up electron. We'll do a half arrow up for that. If I have the very same electron along the same axis, but it's twisting around in the opposite fashion, we're going to now call that spin down and half arrow down. Outside of the atom, the electrons can switch spin, no problem. But what's going to happen here is, as we start referring to these orbitals as actually rooms where electrons can sit in, if someone has gone in and was a spin-up electron, before the other electron can pair with it and get close to the nucleus, it has to make sure it has a downspin to go in as a downspin. It could very well be the downspin that goes in first, but just for convention's sake, we always put the upspin going first. Remember, outside the orbital, the electrons can switch spin, no problem. These sort of diagrams, maybe this is a 1s room here, these sort of diagrams are referred to as arrow in box diagrams. The box represents the kind of room that we're in, and the arrow indicates not only each arrow is a separate electron, it indicates the property of spin that it has. So, with that in mind here, with those two rules, we're going to look at a few examples. I know this part here is getting a little bit weird, okay? But let's start off here, super simple with hydrogen. I like hydrogen because it only has one electron. The Bohr model perfectly well predicts this. So hydrogen, I'm not going to necessarily worry about the nucleus, but hydrogen has an infinite number of shells available. We are going to off-Bohr. We're going to say, if we're the one electron, where does the electron end up? The electron will always go to the closest position available to it. So, we have the electron on n equals 1. On our energy level diagram, so far we had shell 1, shell 2, shell 3, like this. Okay? Well, I know I have all these rooms available, but if I can sit on shell 1, I may as well sit on shell 1. In our electron configuration model here, I've been saying shell 1 is low energy. It doesn't actually subdivide into the 1D, 1F kind of layers. On shell 1, you only have an S kind of room. So in a similar fashion here, the one electron is going to go into the 1s room, and we're going to actually write that in the new electron configuration model. Hydrogen has the configuration 1s1. The big number 1 here refers to the energy level n. The S, this part here, will refer to the kind of room. The fancy language here is we're going to say the orbital. This is the type of room that we're in. It's either going to be S, P, D, or F. This part here that looks like a power, do put it as a subscript, so do put it as a sort of higher up number. This part here just refers to how many electrons. In this case here, in my floor number 1, S kind of room, we only have one person there. That's why we're 1s1 as our configuration. So, that's all we have for hydrogen's electron configuration. Let's get a little bit harder here. Every element will have its own number of electrons. Let's take beryllium as an example. Beryllium, if you look at your periodic table, has 4 electrons. We're going to start seeing the breakdown of the Bohr model. So for beryllium, we have an infinite number of shells available. Although every element will have its unique number of protons, the energy spaces may be different. We talked about that in our emission spectra, absorption spectra. Every element will have shell 1, shell 2. Every element will have electrons. Entering this, try to be as close as possible. We talked about the first two going into the first shell. Those are the best places for it, closest to the core. The third electron is out of luck. First shell has maxed out. The third electron then goes in. It's going to go in single. The next electron goes in single. As we compare that to our new electron configuration model, we're actually going to see that it's not quite correct that these two electrons are actually separate. Whenever it comes time to do Bohr model or Lewis models later on, we are going to keep them separate. But here's a part that's not consistent with our new model. Here's what I mean. When we have shell number 1 and shell number 2, shell 1, we talked about it only being 1s kind of room. Shell 2, we saw from earlier, separates into the lower 2s kind of room. Whenever the p kind of room shows up, they always show up as 3 individual rooms. Pauli says each individual room, called an orbital, each room maxes out at 2 electrons. So imagine 4 people arrive at your hotel, you're the manager, and you can put these electrons wherever you want. They all want off-ball, they all want to be ground state, so you're going to put them in. First guy goes in, again for convention's sake, we're just going to go upspin first. Could very well have been downspin, but if we just keep consistent up and then down, it saves a little bit of writing. So upspin goes in first, that's the first guy. Second guest arrives, the whole hotel is free to it. It also wants to be close to the core, so second guy, even though it doesn't really like this electron that's already there, it's going to go in, ensuring that it has a downspin. Third electron realizes, well, this room here is maxed out. This room here can only handle 2. I need to take the elevator up to floor number 2. All of these orbitals here, the 2s and the 2p, are all on the same floor, technically, but because there's different types of room, maybe one room, the S room has 1 bed in it, maybe a P room with 2 beds in it, we actually need to differentiate which kind of room that we're in. Because the S is lower energy, when that third electron goes in, it's going to end up going into the 2s room, no problem. And here's where we start seeing the first distinction. In the Bohr model, we see that they actually go in separately. In this case here, the fourth electron, when they go in, even though energy level 2 is the next available spot for it, the fourth electron will not prefer to go into 2p because that's higher energy than it could be. The fourth electron will actually end up pairing with the first one. So in that case there, our electron configuration model, this is paired up, whereas in the Bohr model it's not paired up. That's fine. We still want to list the configuration here. So in this case, it's going to start looking like gibberish. Basically, it's a roster of where all the electrons end up. In this case here, we have 1s, 2. On floor number 1, the S kind of room, there's 2 people. Those are those 2. And then we're going to follow it up with 2s2. On floor number 2, the S kind of room, likewise, we have 2 people. When I add up all these subscripts, they should add up to the total number of electrons in the element because I have a roster of where I put everyone. There's one last rule that we're going to see with this electron configuration model, which is oxygen. So oxygen, as an example, we have 8 electrons, so we check the periodic table. The Bohr model, again, it's a little bit simplified. It doesn't give you the distinction between 2s and 3s. So first 2 electrons go in. Again, I want to emphasize for the Bohr model, even though the electron configuration model predicts we're actually paired up, we still do the Bohr model as we're used to. So those are the 8 electrons that oxygen has. Let's see how this ends up showing on the electron configuration model. So far we only have 8 electrons, so I don't need even shell 3 yet. So this is just shell 1, shell 2 is separated into 2s and 2p. Oxygen's energy levels will be different from, say, beryllium's, but every element will have the same ordering of orbitals as this time we have 8 people arrive at the hotel. We always want to off-ball, we always want to start lowest energy first. So the first 2 go in, 1s, so 1 upspin, 1 downspin. The next 2 go in, remember every arrow is an electron, 1 upspin, 1 downspin. Now strangely enough, the 5th electron in, the 2s is now full, the next lowest energy spot available is the 2p. The 5th electron goes in, there's 3 of these kind of rooms on floor number 2, it can take its pick. At this point, the 6th electron has somewhere to choose. These energy orbitals are said to be degenerate. The 2p orbitals, all of these are degenerate orbitals. I know that's a big word, but degenerate just means equal energy. All of these orbitals are equally good to say. They're all equal distance from the nucleus. There's no preference one over the other. So if you were the 6th electron, you're the next person that's going to be put into the hotel, you actually have a little bit of a choice. Do I go into the room that the 1st electron went in, and do I pair up with them, or do I take my own room? Because both of them involve these degenerate orbitals, both of them involve me being the same distance from the core. What we're going to end up having here is, this is our last rule, we're going to call this Hund's rule. Hund's rule sounds fancy. It basically says, in this situation, electrons will always enter singly. They're always going to enter one by one whenever, it doesn't have to just be these 2p orbitals, but whenever degenerate orbitals are available. So in this situation, when it's equally good to either pair up with this one or be by myself, Hund's rule basically says electrons tend to prefer going in one by one. The mentality that I think about here is your sort of bus mentality. Imagine instead of hotel rooms and like filling in different rooms and whatnot, imagine this was a very short bus. This bus here actually has 3 seats. And as you know, with bus seats, they're always separated too. If you're the first person on the bus, you can take your pick. You can go on any seat you want at your leisure. Again, just for convenience, we just go simply left to right. I could have very well ended up on the very back seat if you like the back of the bus, okay, but you have the whole thing to your disposal. If you're the next person on the bus, there is a seat available for you in that front seat here. But unless you actually know this person, you would probably go to the second seat right away. You can stretch out, you have more leg room and whatnot. In that case although there were 2 possibilities for you, you decide to go to your own seat. Third person goes on, exactly the same thing. Oh, there's only 1 seat left, but at least I can still take my own seat. The only time we actually usually start pairing up is when the 4th person now comes on the bus, realizes, oh, someone has occupied at least 1 seat, then it looks a little bit less strange for you to pair up with the first person. Unlike if it was in the earlier case, if there was just 1 person on the bus and you were the next person on, it would look really strange for you to sit with a stranger when there were so many seats that were available to you. So that's our 3rd rule, which is Hund's rule. As oxygen has 8 electrons, we're going to add these last 4 electrons. I already had 4. The 5th one goes in, 6th one takes his own seat, 7th one takes his own seat, and lastly it takes his own seat. It's one thing to draw the energy level diagram. It's a little bit tedious at times. So what we're going to do instead is we're going to have that listing, that roster where all the electrons end up. How do I show these 1s's here? Because I have 2 electrons there, I'm going to call that a 1s2. I'm going to show these ones here. The next available spot, floor number 2, S kind of room. There's 2 people inside. And even though Pauli says every single room always maxes out at 2, because we actually have 3 of these individual 2p rooms, in total, in the 3p rooms, we have 1, 2, 3, 4 people, where you call it 2p4. This is now your electron configuration for oxygen. On that note there, we're going to work to a bigger element. So let's go to Scandium here. Under the handouts column on the general Google Doc, you're going to see a quick scan of the energy level diagram. I printed it off for you earlier. Again, every element will have different energy spacings. If I have more protons, maybe my shells are closer, all these gases might be different, but at least the relative order, we always fill in 1s, then 2s, then 2p, and so on and so forth. Every element has the same ordering of orbitals. The next question will probably be, am I giving this on a test? No, but don't stress, okay? We're going to give you a hint of how we're going to do this. So I'm going to do one other example with you for scandium. So far I've only suggested to you shell number 1, boring, it only has 1 room. Shell number 2 separates into 2 columns, 2p and 2s. Again, the s is the lower energy shell. Shell number 3 actually separates into 3. We'll see if I can color code this for you here. Shell number 3 separates into 3s, 3p, and 3b. Those are the 3 different kinds of rooms on floor number 3. You'll notice on this energy level diagram there is no x-axis, so it doesn't matter left or right, but just for convenience they're putting the S's, P's, D's, and F's just for easy tracking. Here's where it gets even more confusing. When we start going to n equals 4, shell number 4 is now farther away from the core. It's now even higher energy. Shell 4 does end up separating into 4s, 4p, 4d, and 4f. Okay, so each shell has been subdivided. But what you'll notice here, strangely enough, by the time shell number 4 is actually separated, the 4s actually ends up energetically lower. It's energetically more stable than even energy level 3. So if I were off-balling, if I were adding electrons to my hotel, even though this is technically a floor number 4 shell, a 4s, I'm going to fill in 4s before I start filling in 4d. So I just wanted to show you that part there. We'll do scandium as an example, and then we'll talk about how do we possibly predict which orbital is going to come next. So let's just do that. Scandium has 21 electrons. So instead of drawing the Bohr model and whatever and seeing it break down, we're going to go straight to our energy level diagram. For the time being, you can still refer to the energy level diagram. So shell 1, 1s, shell 2, 2s, and 2p. This was the same diagram as we just talked about. Shell 3, I want to just color code for you. 3s, 3p. When the D rooms finally come in, they actually show up always 5 at a time. And shell number 4, I'm not actually going to need the, say, 4p, 4d, which are even higher energy. But shell 4, by the time it's subdivided, strangely enough, shell 4s, again, like I mentioned earlier, is actually a little bit lower energy than 3. So keep that in mind as we start putting the electrons onto here. So we have 21 people. First 2 electrons go in here. They off-ball, they build up, ground state, lowest energy first. Upspin, downspin. The next 2 go in, 2s. And they're paired up on shell number 2. Then they go in Hund's rule, single, 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 or bus mentality. We have way too many electrons, so we definitely fill up that bus. So far we have maxed out. If you've actually matched it up here, you'll realize the first shell has a maximum of 2 electrons. What do we say the second shell should have a maximum of? We said the maximum should be 8, and there's our 8 electrons. And here finally we have an answer for shell 3. Is it 8 or is it 18? Depends on your context. If you look at the Bohr model, if you look at just the valence electrons, which you'll see are the S and the P's, as we fill in the next guys here, they fill in 3s1, 3s2. We do our Hund's rule, the same bus mentality on fill number 3. At that point there, we would say it maxes out at 8. Technically though, there are other rooms that belong to energy level 3. In total, we have 5 rooms that all max out at 2. There could be 10 potential extra electrons that belong to shell 3, but they're not included in the S's and P's. So if you were counting 8 and 18, you would count 8. If you were just looking at S's and P's, you would count 18 as you start looking at those extra 10. And in the coming lessons, as you start drawing shapes to it, it'll make more sense. Why do we include them sometimes and why not? In this case here, if you just double check my counting here, I should be left with 3 electrons. Where you may be tempted, we're off-balling, just sort of building up from scratch. Before you're able to build into 3D, we actually are going to end up going to the 4s, 4s1, 4s2. Notice that 4s shell gets filled up before the 3D, all because of off-ball, all because energetically it's lower energy than 3D. Again, our electron configuration model, what it's going to do is going to give you a summary, a roster of where everyone ended up. So I'm going to start off. It's going to look fairly long because I need to include all 21 electrons where they all ended up. So we have 1s2. In this case here I have 2 people in 2s, 2s2. I have 6 people in 2p, so we just put them together as 2p6. 3s also has 2 people inside. Upspin just conveniently goes in first. 3p also has 6 people. In this case here, because the 4 was lower energy than 3D, the 4s, we're going to have 2 people inside, and then finally we're going to have 3D. By the time the D's end up showing up, it actually ends up after we have filled in 4s. And here's just a quick caution. The left and right order doesn't matter. I could have written this last little bit here. I could have written it 3D1 first, then 4s2, because if you look at the numbers, I still notice that I have been filling in. Notice that the 2s already has 2 people in it. that was completely maxed out before you actually put in the D's inside. IB prefers to put all the numbers together, that way you can track things like 3s2, 3p6. It can say, well, technically these are all energy level 3, even though I know this last electron is out. The one last thing I'm going to end off with here, how do we predict these shells if we're not given this energy over there? If we're not given this hotel and what shell comes up, it definitely gets even more scary up at the top. Nicely, we're going to actually just break up the periodic table into 4 different segments. Let me just hint at it here, and then again you could have this on the window. Based on our periodic table, let's sketch it over here. Based on our periodic table, it has this sort of rough shape. We're going to separate this into 4 main sections. For the purposes just of this memory aid, I want you to imagine helium was just moved over here. Some periodic tables actually have it over here. In that case there, we can actually separate into the 4 different segments. Our first 2 columns, alkali metals, alkaline earth metals, we're going to refer to these as S block. Any electrons going into there are S's. The last 6 columns, starting from boron all the way over to neon, the last 6 columns, this block here is going to be P block. We only get into the D's when we get into the transition metals, so these are into a D block. The 2 rows that we end up pulling out of the periodic table, more on this in the next lesson, the very last rows. So we use the same letters S, P, D, and F to actually figure out which is the order reference. S's and P's are super simple. S's and P's will follow the row number. So row number 1, hydrogen's row. This is row number 1. If I were asked what's the configuration for hydrogen, I would look where it is on the periodic table. It's on row number 1. It's in the S column, and it's the first element in. Hydrogen will right away have a configuration of 1s1. It's the only electron that we have. Helium in a similar way, row number 1, still an S block, but because it's the second element in, helium would then be 1s2. Earlier we did beryllium as an example, we can just double check our work. Beryllium is sitting on shell number 2. It is still sitting in S block, and it's the second element in. I should have beryllium as the very last electron. I should have it as, say, a 2s2. Row number 2, we're in S block, but we're the second element in. Because a full configuration shows you all the electrons, though, we don't just show where the last electron ended up. We have to basically start from hydrogen. Hydrogen and helium's electron would go 1s1, 1s2. The 1s2 is completely filled. Lithium is 2s1, beryllium is 2s2, and there we go. We verified beryllium should only be 2s2. If you start going to oxygen, we're also on row number 2, so I'm expecting energy level is 2. If you count the number of boxes in ion, oxygen should be the 4th element. So because I'm row number 2, I know I'm energy level 2. Because this is P block, our orbital is now going to be 2p. Boron would be 2p1, 2p2, 2p3, oxygen is then 2p4. Building up from hydrogen all the way to oxygen, we should end in 2p4. If you double check our work from earlier here, there we go, oxygen right away. So you see, based on the way the periodic table is arranged, we can actually figure out which is the order that comes next. When we complete this memory aid here, you're going to have no problem coming up to this one here as 4s. By the time the D's first show up, which is your transition metals, just for the purpose of this memory aid, I just want you to memorize, even though this is technically row number 4 on the periodic table, the D's are 1 row shorter. We're going to have 3 D's, and therefore if you just look closely here, as I'm adding out, as I'm counting over, we will end up filling in a 4s1, 4s2 before we get to our 3d1, just like we talked about. So energy level 3 starts at 1 row shorter. So similarly 5s, that'll be linked with the 4d row. 6s will be linked with the 5d row. By the time the F blocks finally show up, similarly I just want you to memorize the F's show up at 4f first, and then 5f, and that way you'll have memorized this chart here without actually having this stated. So on the back side of the handout that I'm going to give you here, that's that memory aid again. The S's and P's are awesome. This one here matches up to the row number. By the time the B's first show up, notice these are energy level 3, and by the time the F's finally show up, we'll have energy level 4. It's technically row number 6s. 5D is going to be the transition metals. We were already 1 row shorter, but by the time the F's actually get pulled out, the 4F's actually show up at energy level 3. just for practice, I'm going to give you just 2 elements I want you to try out. I want you to see if you can write. This is how the questions usually worded. Write a full electron configuration. Show me where everyone ends up. Write a full electron configuration for aluminum. And do a full electron configuration for, let's find out the table here. It could very well be anything. If you want to challenge yourself here, try, you can go over those some. Thanks guys.